At the end of this video, I hope that you can explain how the shapes of molecules are accounted for by hybridization theory. Chapter 6, Section 5, Hybridization. VSEPR theory is useful for explaining the shapes of molecules. However, it does not reveal the relationship between a molecule's geometry and the orbitals occupied by its bonding atoms. To explain how the orbitals of an atom become arranged when the atom forms covalent bonds, a different model is used. This model is called hybridization, which is the mixing of two or more atomic orbitals of similar energies on the same atom to produce new hybrid orbitals of equal energy. Methane, CH4, provides a good example of how hybridization is used to explain the geometry of molecular orbitals. The orbital notation for a carbon atom shows that it has 4 valence electrons, 2 in the 2s orbital and 2 in the 2p orbitals. We know from experiments that a methane molecule has a tetrahedral geometry. How does carbon form 4 equivalent tetrahedrally arranged covalent bonds by orbital overlap with 4 other atoms? 2 of carbon's valence electrons occupy the 2s orbital, and 2 occupy the 2p orbitals. Recall that the 2s orbital and the 2p orbitals have different shapes. To achieve 4 equivalent bonds, carbon's 2s and 3 2p orbitals hybridize to form 4 new identical bonds called sp3 orbitals. The superscript 3 indicates that 3p orbitals were included in the hybridization. The superscript 1 on the s is understood. The sp3 orbitals all have the same energy, which is greater than that of the 2s orbital, but less than that of the 2p orbitals, as shown in figure 6-23 on page 188 of your text or on the screen now. Hybrid orbitals are orbitals of equal energy produced by the combination of 2 or more orbitals on the same atom. The number of hybrid orbitals produced equals the number of orbitals that have been combined. Bonding with carbon's sp3 orbitals is illustrated in figure 6-24a on page 188 of your text or on the screen now for the molecule of methane. Hybridization also explains the bonding and geometry of many molecules formed by group 15 and 16 elements. The sp3 hybridization of a nitrogen atom yields 4 hybrid orbitals, 1 orbital containing a pair of electrons and 3 orbitals that each contain an unpaired electron. Each unpaired electron is capable of forming a single bond, as shown for ammonia in figure 6-24b on page 188 of your text or on the screen now. Similarly, 2 of the 4 sp3 hybrid orbitals in an oxygen atom are occupied by 2 electron pairs, and 2 are occupied by unpaired electrons. Each unpaired electron can form a single bond, as is shown for water in figure 6-24c on page 188 of your text or on the screen now. The linear geometry of molecules such as beryllium fluoride, BeF2, again refer to table 6-5, is made possible by the hybridization involving the s orbital and 1 available empty p orbital to yield sp hybrid orbitals. The trigonal planar geometry of molecules such as boron fluoride, BF3, is made possible by the hybridization involving the s orbital, 1 singly occupied p orbital, and 1 empty p orbital to yield sp2 hybrid orbitals. The geometries of sp, sp2, and sp3 hybrid orbitals are summarized in table 6-6 on page 189 of your text or on the screen now. At this point, I hope that you can explain how the shapes of molecules are accounted for by hybridization theory.